Hello, everyone. So in this lecture, we're going to talk about forced convection transfer over flat surface. So up to now, we talked about conduction transfer, and we used the general form of Newton's law of cooling to calculate the convection transfer. But in our equation for the Newton's law of cooling, we also have some approaches to calculate H in here. So the question is how the H is calculated. We have two forms of Newton's law of cooling. This form gives you the convection transfer rate at certain location, at certain point. So this is a local value of convection transfer rate, the first equation. The second one is the overall convection heat transfer rate. So this one is over a certain area. This is for a certain point. That's why when you use this equation, you need to use local value for H. And when you use this equation, you need to use average value. This is a very important difference. And the second one is in power. The first one is in power per unit area. H, as I said, is convection transfer coefficient, local or average, depending on the equation that we want to use, and depending on what we are asked to calculate for in the problem. A sub S is the heat transfer surface area. T sub S is the temperature of the surface, and T sub infinity is the temperature of the fluid sufficiently far from the surface. So the H depends on so many factors. Depends on whether we have turbulent regime of the fluid flow, laminar regime of the flow, what is the roughness of the surface, is it a smooth or is it rough, what is the roughness value. So there are so many factors, the temperatures, the pressures, all the factors, type of fluids. Now, so just let you know, the difference between H average and H local is this. So this is how we typically, generally, we calculate average value of H. Okay, let me put a bar sign in here. So let's say you have a surface with a constant width and the length that is L, and let's say X is in this direction, from 0 to L. Okay, and the total area is A sub S. So the general formula for the calculation of overall H value or average H value over the entire length, over the entire surface is this, 1 over A sub S, integration over entire surface of the local value dAs, or 1 over length, because width is constant, 1 over L, 0 to L, local value, or the H sub X times dx. So local value of convection transfer coefficient at each X position. Now, the convection transfer, as you remember, involves fluid motion and heat conduction. You remember that first we need to have the interactions between different molecules, different particles inside a fluid, or between the fluid and the solid surface, to have the bulk motion, to have the convection. So first we need to have the direct interactions between the molecules in the form of conduction transfer. Then, as a result of motion that is called advection, the combined mechanism is called convection transfer. So advection, the motion of the fluid that can be forced or natural, and conduction at the surface, at the interface between fluid and the solid material. So we have a bulk motion that is called advection and conduction between the surface molecules and the fluid molecules. And this can be natural or forced form. So the conduction that we say typically is as a result of this effect. There is a condition that is called no-slip condition. No-slip condition means a fluid in direct contact with a solid sticks to the surface due to the viscous effect, and there is no slip. So if the fluid is flowing over surface, for example, in this case here, the fluid particles right adjacent to the surface, to the solid surface, have the same velocity as the velocity of the surface. So if the surface is stationary, then the fluid also have zero velocity, fluid particles. If surface is just moving toward the right-hand side or the left-hand side with certain velocity, let's say 2 meters per second, then the fluid particles also have the same velocity at that position, at that elevation, at the solid surface. This is very important. So that's basically why we have conduction transfer between the solid surface and the fluid above the solid surface, on the solid surface, because they stick together and they don't move with respect to each other, so they have direct interaction. Then from that fluid particle to the above particle, from the particles above the surface, we have advection and bulk motion. So the reason that I'm mentioning no slip condition in here is the fluid particles right above the right on the surface does not move. They cannot move. So we have conduction mechanism. What is boundary layer? Boundary layer is the region inside the fluid flow where we have viscous effect. And basically, actually this is velocity boundary layer. So this definition is actually for velocity boundary layer. So the velocity boundary layer, let me mention it in here. Velocity boundary layer is the flow region adjacent to the wall in which the viscous effect are significant. So as a result of viscous effect, we get velocity distribution. So before heating the surface, the fluid velocity can be uniform. But after starting moving over the surface from this point at x equal to 0 forward, the velocity above the surface changes from 0 because of the no slip boundary condition, or if the plate is stationary, from 0 velocity to the original velocity. This is called velocity distribution, and up to the point where we have velocity change. So it seems like velocity changes up to somewhere in here. At this point, so this is the thickness of the boundary layer. And the thickness of the boundary layer increases. Okay, so this is velocity boundary layer. Also, we have thermal boundary layer. So velocity boundary layer, as you can see in here, it happens as a result of velocity difference between the fluid that is moving and the plate. Plate is stationary. Also, we have thermal boundary layer. Thermal boundary layer happens as a result of different temperature difference between the fluid and the surface. So let's say velocity, so the temperature before the fluid heating the surface, the cold surface, let's say, is 100 degrees Celsius. And the temperature of the surface is 20. When it hits the surface, the fluid loses energy at the layers closer to the surface, the solid surface. So its temperature in the area closer to the surface is lower than the original temperature because it's losing energy. This area where we see the gradient of temperature or change of the temperature in vertical direction is called the thermal boundary layer. So these shaded area, blue shaded area, is called thermal boundary layer. And this length, the length across which we have vertical lengths across which we have temperature gradient, or basically temperature change with respect to y direction, is called thermal boundary thickness, or delta sub T. And here, this is called delta. We don't want to really calculate delta or delta sub T now in this lecture. So this is called thermal boundary layer. But we're going to work more we're going to have some temperature distribution, and we're going to also use this concept in here, no slip conditions, to derive some equation. So this is the equation. Since at the surface, the fluid particles do not move, they stick to the surface, solid surface, as I said, the mechanism of heat transfer is only conduction. Conduction inside the fluid, not the solid surface. Because inside the surface, obviously, inside the solid surface, we have conduction. So we can write the energy balance. Energy balance says that, so if this is a surface and you have fluid above that, you have heat transfer. Let's say the surface is hot. So at the very first layer, you have conduction, then you have convection. And if you have a steady state situation, whatever coming should leave to a certain layer. The flow of heat through this very first layer is conduction, and the form that is leaving, the form of heat transfer, is convection. So these two must be the same. So at the surface, we have conduction, and it moves toward inside the other layers of the fluid in the form of convection. So convection heat transfer can be calculated as case of fluid times the temperature gradient at the surface at y equals 0. This is a y direction. Okay, this is basically the Fourier's law, but Fourier's law of conduction for fluid, not the solid material, because fluid at the very first layer works as a solid substance, solid medium. So convection heat transfer is equal to whatever that we get from at the surface, right? At the surface, the heat transfer is actually conduction and is calculated according to this equation. You remember that negative sign times K of the substance of the medium times the temperature gradient at that point. Here, the temperature gradient is actually the temperature gradient of the fluid at the surface, right on the surface. So, and also convection heat transfer, according to this equation that we had in here, is h times Ts minus T infinity. We're gonna use the local value, right? So this is equal to h times T of the surface minus temperature of the fluid far away from the surface. If I set these two equal, I get this equation. And this is a very useful equation. So convection transfer of a fluid flow is equal to minus sign times conductivity of the fluid, conductivity, not convectivity. Because convectivity is already this. Conductivity of the fluid that can be read from the table at certain temperature times the temperature gradient at y equals 0 at the surface, temperature gradient inside the fluid at the surface divided by Ts minus T infinity, and has a unit of watt per meter squared, degree Celsius or meter squared Kelvin. They are the same. This is very interesting and very useful equation, and they use this equation basically to measure and to calculate the convection transfer coefficients experimentally. So the average and mean convection transfer coefficient that I mentioned in here is calculated according to this equation, by the way, this equation. Average values. Okay. Now, so convection transfer coefficient has a dimension, watt per meter squared Kelvin, watt per meter squared degree Celsius. It has a dimension. So if you measure that for certain geometry, for certain surface, then you can use that value only for that specific surface or conditions for that fluid. But in mechanical engineering, in thermal analysis, thermal fluid systems, we want to have general picture, big picture of the convection transfer mechanism. And that's why we want to work with dimensionless or non-dimensionalized form of the equations. That's very helpful, because non-dimensionalized form can talk about different geometries or similar geometries, different thermal conditions, is more general. That's why instead of using convection transfer coefficient, we use Nusselt number. Nusselt number is defined as this: h times some characteristic lengths divided by conductivity. So what are these? H is convection transfer coefficient of the fluid. L sub c is some length that is a good representative for that specific geometry, for that specific shape or surface. K is conductivity of that fluid. And now see what it means. So let's say you have lower surface, upper surface, and in between you have fluid layer. And also there is a temperature difference. Let's say T2 is larger than T1. So there is a temperature difference, then there should be heat transfer from upper side to lower side, right? Now, let's look at these from two different perspectives. Let's say fluid is working as fluid is not really moving in vertical direction. and is just working as a solid medium. In this case, the heat transfer is only happening in the form of conduction. This is the conductivity of the fluid. What if fluid is moving very well, significantly? Then we can model the heat transfer in the form of convection. So it really depends if the fluid is really moving that much or not. So we can model this heat transfer with these two forms, with these two equations. This tells us that this gives me heat transfer in the form of conduction through the fluid, and this gives me heat transfer in the form of convection through this fluid. And we have combination of both in most mechanisms. I mean, sometimes one of them is very significant and dominant, the other one is very small, or other way around in different system. So if I divide them, the convection part, convection mechanism divided by conduction mechanism, this is what I get. Actually, Nusselt number. So that's what Nusselt number is telling me. Nusselt number tells me if the convection heat transfer is dominant or not. When the Nusselt number is very high, it means the mechanism of heat transfer is mainly happening as a result of convection, not conduction. And when Nusselt number is small, it means the main and significant form or dominant form of heat transfer, in this example between upper surface and lower surface, as a result of conduction. So Nusselt number is very good representative of the dominance of convection or conduction. So this is the meaning of the Nusselt number. Practice. This is actually example. So it was supposed to be an example problem, but I changed it. It was supposed to be a practice problem, but I changed it to example. So I'm going to solve it for you guys. Then you're going to assign a practice problem. Consider airflow over a plate or a flat surface maintained at a temperature of 220 degrees Celsius. The temperature profile of the airflow is given as this. The airflow at 1 atmosphere has a free stream velocity and temperature of 0.08 meter per second and 20 degrees Celsius, respectively. So by the way, this temperature profile is this. So the temperature profile at each location is this. So if you use that equation, you can draw this line. Okay. So let's say you want to know the temperature profile, let's say at x equal some value, okay, 10 meter. Okay. So you use that equation and your temperature profile is going to be drawn accordingly. Okay, so the temperature profile at each point, at each location, at this location, at this, for example, for this shape, the temperature profile is this. So this is my temperature profile. So this shape, this curve can be plotted using this equation for this specific problem. T infinity, so this is the temperature with respect to y at each temperature temperature at each y position. Temperature at each y position. Okay. This is, by the way, is about a temperature profile at certain locations. So this equation, it just gives you the temperature profile at certain location, not at each location, because it's just function of y, you see? If it was a function of x and y, that would be different. But this is a temperature, this is a profile of y. It means it's talking about the profile of the temperature at one specific x location, let's say x prime, but at different y position. So it doesn't, this specific profile that is given in the problem is not going to give you temperature profile at other locations. Okay. And we're asked to calculate the heat flux on the plate surface and the convection transfer coefficient of the airflow. Okay. So first of all, we need to read the properties. You see, we have the temperature of the surface that is 220 degrees Celsius. And also we have temperature of the air, of the fluid, that is at 20 degrees Celsius. And the fluid velocity, of course. So the question is, at what temperature we read the, because we need the properties. You see here, the thermal diffusivity of the fluid it's needed. Temperature of the surface, temperature of the fluid, y position, velocity. This is exponential term. So at what temperature we need to read the properties of the fluid? At 20 degrees Celsius or 220 degrees Celsius? Well, the fluid particles closer to the surface are gonna be warmer, are gonna be at higher temperature, and temperature far from the surface are gonna be colder. So which temperature we choose? This is very important. This kind of fluid flow is called external flow. An external flow, we read the properties at film temperature. What is film temperature? This is the film temperature, the average of surface and fluid temperature at each position. Ts plus T infinity, 120 degrees Celsius. At this average temperature, we read the properties. What properties we need? If you want to use all the equation that we already developed, we need conductivity of the fluid, not convection transfer. I mean, eventually we're going to calculate it. We are asked to calculate it, but we want to read the conductivity and diffusivity of the air, at that temperature. So we go to table A22 and we read the conductivity of the fluid at 120 degrees Celsius and diffusivity of the fluid at this temperature. Okay, diffusivity has the unit of meters square per second, and conductivity, as you remember, watt per meter Kelvin. Now, we are asked to calculate the heat flux and convection transfer coefficient. If we want to calculate the heat flux, this is our equation, right? Because heat flux at the surface can be calculated using conduction equation or Fourier's law inside the fluid, not the solid material, not the solid surface. So we use the Fourier's equation with conductivity of the fluid and temperature gradient inside the fluid right above the surface at the layer adjacent to the solid surface. Conductivity of the fluid is already read from table A22 at 120 degrees Celsius. What about this temperature gradient? Well, fortunately, we are given temperature profile equation. So we can calculate the temperature gradient, this temp, at y equals 0 very easily. The temperature gradient is, so we need to differentiate, we calculate the derivative of this equation first. This is an exponential term. So its derivative is going to be equal to this. T infinity minus Ts times V over diffusivity of fluid exponential of the term. So this is the derivative of temperature profile. This is the derivative of the temperature profile that is given in the problem statement. This is that was a derivative of this equation. Now we calculate this. So after you calculate the derivative, first you plug in 0. So after deriving the derivative, you set y equal to 0. All other values are given or read from the tables, property table, and this is going to be temperature gradient at the surface at y equal to 0. Now we multiply it by the conductivity, and this is going to be value of the heat transfer rate. This is the local heat transfer rate. This is the heat transfer, convection transfer at the surface at that specific location, or basically conduction inside the first layer of the fluid right above the surface, right on the surface, adjacent to the solid surface. Now, what about the second part of the problem? We were asked to calculate the convection transfer coefficient. Basically, we are calculating the local heat transfer coefficient. Local heat transfer coefficient is calculated using this equation that we developed before the problem. Conductivity of the fluid, we already read that from the table. Temperature gradient at the surface, we already calculated that. Ts minus T infinity. And this is going to be our convection transfer coefficient. Keep in mind that convection transfer coefficient is always positive. So what you're asked to calculate, what you're asked to work on is this practice problem. The upper surface of a 50 centimeter thick solid plate with a conductivity of 237 watt per meter Kelvin is being cooled by water with temperature of 20 degrees Celsius. So temperature of this water here is 20. So this is at 20 degrees Celsius. The upper and lower surface of the solid plate maintain at constant temperatures of 60 and 120. What is the water convection heat transfer coefficient and the water temperature gradient at the upper plate surface? So first of all, you need to read the properties. Keep in mind that you need to read the properties at the film temperature for the water, not at the water temperature, or at the upper surface temperature, at the film temperature. So this is your assignment from this lecture, and have a great day, and stay healthy.